Okay, so we're looking at the connection between free energy and equilibrium. Now, when something's at equilibrium, delta G is zero. And that kind of makes sense because if it was negative for one thing, then it would be positive for the other way. So it has to be zero in order for it to be a reversible reaction. One way we can see this is a change in Q and K. So when we have the two gases of the reactants, it is spontaneous. It's going to make product. It's also spontaneous when we have the the ammonia react to make nitrogen. It's only going to be Q equal to K when it's at equilibrium. So remember, Q is equal to K. That means it has an equilibrium constant, but delta G is zero at that stage. So the reaction we get here is that delta G is going to be the standard delta G plus the R constant times the temperature times the ln of Q. So this would be some non-standard condition, which kind of makes sense because it wouldn't be at standard condition. If it was, then all of this would be equal to zero because Q would be equal to K, in which all that would cancel out and they'd be equal to the same thing. But Q is not at equilibrium. So equilibrium point occurs at the lowest value where free energy is available to the reaction. Therefore, delta G is equal to zero, Q is equal to K. So when we think of these things, if K is bigger than 1, delta G is less than 0, more spontaneous. When K is less than 1, delta G is going to be positive at standard conditions. So we're really trying to get this idea down that when it seems products are favored, delta G is more, it happens to be spontaneous. When reactants are favored, we look at it being non-spontaneous. So if we were trying to relate these together, delta G under non-standard is equal to delta G standard plus Rn ln of Q, RT ln of Q. Delta G is 0. That means K is equal to Q. 0, solving. Delta G under standard conditions is the negative RT of ln of K. And remember, your R value given on your thing is this R value, not others. If you use Hess's law style for the Gibbs problems, to where you have the multiple reactions that you have to eliminate kind of intermediates and add together, you remember that you need to do the same with your K value as you add and multiply. So when you multiply an equation, like all times 2, you need to raise that K to the exponent. If you double the reaction, K squared, half the reaction, square root of K. Adding reactions at the end, multiplying all the K values. You might remember these components that we talked about this briefly, but you're like, I don't think we ever really did it much. Here's why we're doing it. So the K's overall will multiply all together. Then you can do things like this to where the delta G is equal to all of these. So if we have this occur, and then we have this occur, we can put the two together to where we can make all of these things occur, right? And keep in mind, we can't eliminate T on both sides because there's no T part here and this is being subtracted. So be cautious, you can't just dump out T in order to get that. However, you can see the multitude of these concepts here to where you can determine a lot of different values, just like you can do with any algebra equation. If you know everything else, you can determine any other constant, any other variable. So we've got this concept here. You can rearrange and solve for the ln of K, much like what we have this depiction here. So the ln of K is proportional to 1 over T. And if we were to change that to a y equals mx plus b situation, we could see that you can find delta H and delta S by graphing alone. Okay, we wouldn't do that maybe on a lab or something, but this would be a little bit past of what you would do for an AP test. But this really shows the multitude of what you do in college and the idea that you can determine these factors from graphing, which is often what they are doing in multiplying and dividing and determining K values in a chemical equation. So likewise, you would graph ln of K divided by 1 over T, because that's your X, best fit line, slope, intercept. You can see that there's so many arrangements. Arranging, substituting, solving when it comes to this. This is why you got to have some decent algebra skills, and you should be at your best right now because it's the end of the year. So the best advice, if you're not strong, over and over until muscle memory. The problem with some of these, though, is that you really need to be comfortable enough to understand it because you never know what you're going to get as a possible question. Every time you have a question that requires a different equation, write it down. Make your own little cheat sheet. I kind of got you started here. So if you got your delta G, that means K is equal to the E to the negative G RT. You also know your delta G as this here. Now, so many possibilities. You might know K, determine the temperature when it's thermodynamically favorable, meaning delta G is -0. And again, that would be asked in a question that's not so legitly explicit. You know, they might say thermodynamically favorable, where you need to remember delta G is less than 0. Given a Q, and if delta G is telling if it's going to be spontaneous or not, based upon knowing what your Q is, they can get really complicated, and you got to really expect that in any real AP test. So doing a multitude of practice just gives you the opportunity to see these. And again, when you come across these are also going to include electrochemical cells, which we'll continue to talk about in the upcoming sections. Let's just look at a few examples. Again, can't show you all, otherwise you'd be here till next year. Calculate the boiling point given this equilibrium reaction, giving you some LHs and S's. Now, this is a phase change, which you should understand is at equilibrium. So delta G is equal to 0. Since delta G is equal to 0, you have your H's, right? Your change in H, in order for you to calculate that on your own. Change in S, you can calculate that on your own. And again, solving for T, we'd see it at 284 Kelvin, which would tell us the boiling point of this substance based upon the H and S values. Under standard conditions, at your 1 atmosphere, 25 degrees Celsius kind of thing, what will be formed? Given your delta G is positive. Now, thinking of your delta G being positive, that must make you think, well, what's your K value going to be? How's that going to be related? What's good? Is K going to be higher than 1 or less than 1? Okay. So then you also have to think of how you have as your questions, right? So this is all reactants. This is products. This is equal amounts, need more information. Well, if delta G is positive, it's not spontaneous in the reverse direction. Therefore, reactants will be produced, not products. Okay. So thinking about this and the idea, we have to keep in mind that we'll have a whole bunch of NH3 because delta G is positive. So I made a little change. After I said it, it didn't sound correct. Delta G is positive, so it's only spontaneous in the reverse direction, because in the forward direction, it's not spontaneous to go from reactants to products, which means the reverse reaction is true. So the reactants will be produced, not the products, which is why we have NH3 being formed. Now calculating the equilibrium constant, same idea. We have a temperature, we got a delta G. We're going to use the different equation. Delta G, again, we need to make sure our units are consistent. This is in joules, so we need to change this to joules. 298, solve, do your little math, and we get K is very small, which goes in line the idea that we're going to have a whole bunch of reactants and not much products, being K being very tiny at this temperature. All right, so we're going to get to do more examples and things on Pearson. So come in with your questions, and I'll talk to you later. Take care.